Okay, so let's continue the discussion on the ENSO interaction with other basins in terms of anthro influence and influence back on ENSO, and then also bring in AMOC. As you know, as I said before in the last podcast, I'm being supremely brief, so please go and read the article, which is very nice, by the way. The influence of ENSO on the tropical Indian Ocean on interannual and decadal timescales. Many papers have been written on this, so you can see the references also, even though this is just the first paragraph and that's the last paragraph of this section. ENSO induces delayed warming or cooling of the tropical Indian Ocean, reaching a maximum several months after the El Nino peak, as we saw, as we will see. Oops, yeah, figure 3. Yeah, this is figure 3 here. So this is in MAM of 2016, and the peak was in DJF of 2016. Okay, that's the Indian Ocean Basin Mode IOB. This basin-wide SST response is the leading mode of the Indian Ocean SST variability, referred to as the Indian Ocean Basin Mode or IOB mode. IOB is primarily caused by variations in surface heat fluxes resulting from adjustments in the pan-tropical atmospheric circulation during ENSO events, and then there is a feedback to ENSO. Specifically, when El Nino develops in the tropical Pacific, the eastward displacement of the Walker cell suppresses the precipitation and forces anomalous surface divergence over the broad region of, so basically it's explaining what we said. Yeah, this one, okay. Do I need to say more? There is a decrease in cloud cover, which increases shortwave radiation, and the decreased wind speed reduces latent heat loss, and this leads to SST warming. So in addition to wind speed, reduced air humidity differences associated with the tropospheric warming may decrease the latent heat loss over the regions of atmospheric convection. May decrease means we still don't have a good final answer on that. So jumping ahead, finally, the relationships among ENSO, IOB and IOD, so Indian Ocean Basin Mode and the Indian Ocean Dipole, fluctuate on multi-decadal timescales. She et al. Showed that the IOB response became stronger and more persistent with the amplitude and duration of the ENSO events after the 1970s. In contrast, the IOD response weakened after the 2000s. Which is likely associated with the increased occurrence of the Central Pacific El Niños, likely. So again, speculation. The recent weakening of the ENSO-IOD relationship was potentially forced by an upturn in Atlantic multi-decadal variability, which weakened both ENSO and the sensitivity of the eastern equatorial Indian Ocean to ENSO by modulating the background climate via atmospheric teleconnections. So now you are basically reaching in many directions, all with a bit of speculation. Intriguingly, multi-century ENSO and IOD indices reconstructed from paleoclimate proxy records display coherent multi-decadal amplitude modulations, indicating their strong coupling. Okay, so they interact, but the interaction depends, on various other backgrounds like AMV, so there is decadal variability in the interaction itself. Quite complicated, right? As I said, if the models were perfect, you could run models for many centuries and look at these to understand the details of the processes, especially the role of the oceans and role of the Indonesian through flow, for example. On ENSO timescale, we don't talk much about the Indonesian through flow, but it's clear that Indonesian through flow has many impacts on the Indian Ocean. So what is its role in the low frequency interaction between the Indian Ocean and the Pacific Ocean? And so especially here we are mostly talking about atmospheric bridges and hardly anything about the Indonesian through flow, which I think is a big gap in our understanding. Influence of the tropical Atlantic on ENSO. Then studies have suggested that the tropical Atlantic can influence ENSO evolution, which we saw already in figure 3b, and also there is a northern tropical Atlantic playing a separate role. My guess is the ITCZ connects the northern tropical Atlantic to larger scale meridional variability. So the variability in the tropical Atlantic is dominated by Atlantic Niño, which is characterized by SST variability in the central and eastern equatorial Atlantic on interannual time scales, peaking in JJA. This pattern tends to peak in boreal summer with a secondary peak in winter, which is also been reported October-November peak. The primary peak in summer is considered to influence ENSO through changes in Walker cells and the equatorial Pacific trade winds, thereby contributing to the evolution of EP-ENSO events. Again, EP-ENSO is also strongly argued to be connected to the North Pacific meridional mode, and what is the role of the ITCZ in that, and what is the role of the Atlantic response or feedback on the ITCZ. So these are not always very well answered. This influence may occur via an atmospheric pathway over the Indian Ocean and involves interactions with the Indian summer monsoon and maritime continental convection, so all heat sources may be involved. The importance of this influence has been debated, so there are papers suggesting that this may be a statistical artifact, but the conclusions remain under debate. Okay, influence of the Indian Ocean on ENSO, many papers on this already. Indian Ocean variability driven by ENSO or mechanisms internal to the Indian Ocean affect the evolution of ENSO events. In particular, the IOB accompanying ENSO forces atmospheric Kelvin waves into the western equatorial Pacific, inducing surface winds that terminate ENSO events. Interbasin negative feedbacks is more effective for El Nino than for La Nina, so there is asymmetry, as I mentioned before, and enhances ENSO predictability in the ensuing year. IOD has a less clear influence on ENSO because SST anomalies of opposite signs interfere with the forced atmospheric Kelvin waves, so some details there. However, IOD can significantly impact the western Pacific surface winds through atmospheric convective feedback over the maritime continent, enhancing the development of concurrent ENSO events and their predictability. So some arguments have been made. So you have to keep looking at the El Nino predictions themselves, and if there is a skill limitation of UN 0.8, then 20% of the times you are missing things, and we are always interpreting these interactions and feedbacks based on very few samples. Okay, so keeping all that in mind, furthermore, IOD may affect the development of a subsequent ENSO events and their predictability via changes in the western Pacific winds and Indonesian through flow, which is finally mentioned. This IOD influence is the strongest when the western pole is strong, leading to a well-developed IOB. Similar to the influence of ENSO on the Indian Ocean, its influence on ENSO varies on multi-decadal and longer time scales. So the warming is not always, and basin-wide in the same sense, because there are peak warmings elsewhere, and it matters because convection, if convection is triggered by the SST anomalies, then you are likely to have, in larger influence. Sorry, I lost my thought there. If SST anomalies induce convection, then it's easier to influence the atmosphere and generate waves and affect remote regions and so on. Okay, did I skip this? No. Okay, I've been through this. Okay, tropical basin interactions on decadal variability and climate change. As you go to lower and lower frequencies, you know that everybody is talking to everybody. On interannual time scales, there may be few people reaching in because the time scales matter. Whereas if you go to decadal time scales, then everybody has an influence, right? Tropical basin interactions in decadal variability and climate change, then the tropical Pacific climate varies on decadal and multi-decadal time scales. We have discussed this elsewhere in multiple podcasts. Similar to ENSO, this variability is accompanied by ocean atmosphere anomalies in the extratropical Pacific, tropical Atlantic and Indian Oceans, in contrast to ENSO, which primarily arises from the tropical ocean atmosphere interactions. The origins of Pacific decadal variability, which we will see in a minute, which shows the same sign anomaly in the tropics propagating along the west coast of the Americas to the subpolar regions, and opposite signs of anomalies in the Midwestern part of the subtropics in the Pacific remain debated. In other words, is it just a superposition of El Nino and La Nina and their asymmetries producing a low frequency rectification, or is it an independent coupled mode of some sort? That's not very clear. Okay, so they remain to be debated, particularly where was I? Yeah. The Atlantic Ocean also exhibits pronounced multi-decadal variability called the AMV, which is characterized by the same sign of SST anomalies in the North Atlantic and the opposite sign of SST anomalies, albeit much weaker in the South Atlantic. So that's also shown in the next figure. AMV has been linked to fluctuations in the AMOC and the associated northward heat transport, although the relative roles of internal variability and external radiative forcing are still debated. So is it internally generated by ocean-atmosphere interactions and memories, or does it need this greenhouse gas forcing in some ways to make it happen? Lack of data doesn't allow us to answer that question, and models may not be good enough. The amplitude of these anomalies can be very tiny. PDV and AMV both profoundly impact climate and marine and terrestrial ecosystems worldwide. Furthermore, the relative phases of PDV and AMV have constructive or destructive influences on the regional climate. They can add together and make life miserable, or they can cancel each other. So here we go quickly at the patterns. Here is the Atlantic multi-decadal variability dominated in the northern hemisphere with a weaker signal in the south. There are associated signals elsewhere also, even though focus is here. PDV, on the other hand, you can see that it has a El Nino-like signal here, but has this arm going here, and this one with the basin mode kind of signal here, and some strong signal here. So you can imagine, it's been argued also that El Ninos and La Ninas are not perfectly symmetric. So when you add them, they don't necessarily cancel each other. So maybe they leave a low frequency rectification, but you can see this signal here is weaker. This relation seems to be stronger. And what is the role of the Indonesian through flow in these things? That's not clear. So AMV index, multi-decadal variability. So here is a negative phase, positive phase. We mentioned this negative phase already, and now we are in a positive phase as of 2025, I think. These are smoothed, so you have to be careful. They also tend to have higher frequencies. So you can see that explained variances are from the EOF 56.3%, but that's on a filtered time series. And this is 42.1%. Again, decadal, multi-decadal time scale here as well. Okay. Increasing evidence indicates that observed AMV is strongly influenced by external radiative forcing, so it may be something to do with anthropogenic forcings. Intriguingly, some models reproduce the concurrent cooling of the tropical Pacific when forced only by anthropogenic aerosols. So there's a debate about, when you say anthropogenic forcing, it can be greenhouse gases, but also can be aerosols, but also volcanic aerosols, which is also an external forcing, because it's suddenly spewing out stuff that is hidden under the earth from the atmosphere. So it's not man-made, but it's still external forcing. Okay, so basically that debate continues. So recent study argues that SST restoring experiments used to examine the Atlantic influence overestimate interbasin linkages, so model deficiencies are always something to worry about. Nonetheless, Atlantic influence has likely been enhanced by external forcing in recent decades, likely, so we don't know clearly, providing a source of decadal climate predictability. So if there are things that persist, then can we use it to predict things? Given the significant climate impacts of PDV and AMV, it's critical to further understand how external forcings affect these modes of low-frequency climate variability and their interactions to reduce uncertainty in decadal predictions and future projections. I'm a big fan of decadal predictions because projections out to 2100 may not be as useful, but decadal predictions can serve a lot of policy and strategy decisions. Okay. The AMOC, AMV, and the interactions between AMOC and tropical variability. So now you try to pull everything together. I will read just the first paragraph. As AMOC is believed to be a major tipping element in the climate systems, I'm not a big fan of these tipping elements, but we know they are there. Its stability, AMOC's stability, has been the subject of numerous studies, many studies. The response of the AMOC to anthropogenic climate change is another debated topic. Understanding the mechanisms of AMOC variability and its response to climate change requires an understanding of the oceanic and atmospheric teleconnections that modulate AMOC on decadal to centennial timescales. Just remember that AMOC itself is an integral, and models have to integrate through a lot of things, simple things like, well, highly uncertain things like vertical mixing, and then lots of other things. Okay, so we'll see the figure in a minute. But so first, review the paper reviews AMOC variability and so on, and the impacts of AMOC and extratropical variability on the tropical basins and South Asian monsoon variability are discussed. And now there are papers arguing that the Indian Ocean warming is accelerating the AMOC itself. So there are influences going both ways. So I've discussed AMOC elsewhere, so you can follow up. This is the AMOC anomaly. So models are showing something. If you go back to the Industrial Revolution, beginning of the Industrial Revolution, observed estimates are relatively short, and then we go into model projected future AMOCs. Considering all the uncertainties, this is a serious drop in the AMOC. So basically in Sverdrups, the zonally averaged meridional transports, which is shown here. So you can see the figure here in terms of the depth going from the surface to 5 kilometers and going from the southern Atlantic into the Arctic Ocean. So AMOC transect change, large AMOC decline. So you can see that there is surface branches you can barely see, but basically there's cross-equatorial transports with sinking around here, where the Jin Seas, Greenland, Iceland, Norwegian, Labrador Seas, where deep water forms and sinks, and that goes out, spreads into the Southern Ocean, goes into the Indian and Pacific Oceans, comes back. So basically we are constructing these as integrals of many things, which means we are, we can hide lots of model problems in there as well. And this is the large AMOC decline experiments, and this is the let's read the caption to make sure. Historical and future under scenario SSP 585. So it's the business as usual scenario where the emissions are the worst. They project AMOC to get significantly weaker in Series 6 models. B is the time series of AMOC strength from rapid to AMOC reconstructions, an SSD based proxy, and to paleo proxies. So various reconstructions. You have to be careful because local data can be used to do that. So you have 1950 to 2010 or so. Is there a trend? Not much. This is another reconstruction which is longer. This is a shorter one, and this is the these are all observational estimates. So you can just take it that rapid is here, and this is Worthington's paper AMOC in Sverdrups, and this is some other reconstructions, and just look for the numbers. Okay, so not all of them are transports. This is Sverdrups, this is Sverdrups, this is showing Sverdrups. Oops. This is the SPG marine productivity estimate, Southern Pacific. You can leave it as it is. Okay. Basically, we estimate from all the sources possible, and they all differ significantly, so we have to be careful. It's a typical problem, so I don't want to just dismiss it. CND, AMOC multi-model mean stream function contours in historical simulations and its change in colors. So the contours are the historic simulations, and changes or anomalies are shown in colors. So the scale is shown in terms of AMOC strength in Sverdrups. So D, so that's the 4CO2 simulation. So CMIP 5, so CMIP 5 plus CMIP 6 models with large and small AMOC declines respectively. So they are basically taking two classes of CMIPs. CMIP 5 was released in 2014, CMIP 6 of course in 21-22 during COVID, and you can see there are models which show huge changes and there are models which show smaller changes, but these are abrupt 4CO2 simulations. How relevant are they? Depends on what is happening. So if you just look at reality, Greenland ice sheets are melting pretty rapidly and accelerating. Are they increasing the freshwater flux enough to do these sorts of perturbations? Well, there are definitely signals that the region in the North Atlantic where deep water formation happens is not warming as fast or is even cooling. It's called a warming hole. But there are debates about whether anthropogenic impact is in the upstream part of the heat transport across the equator or in the downstream part going from the deep water formation site into the Arctic. Arctic is seen to be Atlanticized, which means its character is changing as well. So I'll leave it there because it's an incredibly complicated topic. The complex AMOC-AMV nexus, then the relationship between the AMOC and AMV is complicated. Origins of the AMV, a multi-decadal alternation of warm and cold basin scale SST anomalies observed in the North Atlantic, have been debated. Over the years, several mechanisms have been proposed, which means we don't have consensus or the clear answer. We don't know the internal variability versus anthropogenic or other forcings like solar and volcanic, which are natural forcings, or greenhouse gases, which are anthropogenic forcing, and of course atmospheric variability that is stochastic. Therefore, the relationship between AMV and internal processes such as AMOC variability or external forcings represents an intricate interplay between SST patterns, ocean currents, air-sea interactions, and changes induced by external forcing. So even if there is an internal variability, the key question may come down to how is the internal variability being modulated by external forcing, right? So those are difficult issues. So regardless of the specific dynamics governing the AMOC-AMV engine, there are multiple indications that the AMV pattern has a far-reaching impact on the global climate system. So this topic raises lots of headlines, produces a lot of headlines, because people claim AMOC will collapse very quickly, and some say no, it's not going to collapse this century, all with these uncertainties in mind. So you have to just be careful about headlines. And the Europeans in general are obsessed with the tipping points, and they keep on saying we are closer to the tipping point than we know. What does that mean? I'm not sure. Impacts of the tropical oceans on the AMOC. I mentioned Indian Ocean impact on AMOC. Enhanced warming of the tropical Indian Ocean is a salient feature of anthropogenic climate change. Modeling studies have demonstrated that this warming can strengthen AMOC. There are two mechanisms by which enhanced TIO warming affects AMOC. First, TIO warming induces an atmospheric planetary wave train to reach the subpolar North Atlantic, forcing a northward shift of the jet stream, which cools the ocean's subduction regions and strengthens the AMOC. So sinking is increased, then the entire supply system also gets stronger. Secondly, rainfall over the tropical Atlantic is reduced because of the strengthening of the Atlantic Walker cell and increased atmospheric vertical stability. On multi-decadal timescales, the resultant salinity anomalies advected to the northern high latitudes, strengthening AMOC. So, in other words, the rainfall changes in the tropical, North Tropical Atlantic, Northern Tropical Atlantic end up affecting AMOC sinking as well. This effect was amplified by the salt advection feedback. A TIO warming of 0.1 degrees C above the mean warming of tropical oceans can amplify AMOC by 1 spheredrup, which is a significant fraction of the general strength of 15 to 20 spheredrups. Thus, enhanced TIO warming could delay the weakening of the AMOC under greenhouse conditions. Indian Ocean is unique because it's getting heat from the Pacific Ocean through the Indonesian through flow. It's directly linked to the Southern Ocean. The atmospheric heating is also working, so it's rapidly warming, and then it may have a negative feedback to AMOC slowing down, okay, by accelerating AMOC. So this is the relationship between the AMOC and internal and external components. So AMOC leads, AMOC lags. So this is the internal variability minus internal AMV AMOC and AMV global. So all kinds of information there. The relationship between the AMOC and internal and external components of AMV. So IAMV and forced AMV here in a multi-model ensemble of CMIP6 historical simulations. So basically they could be pre-industrial into the 21st century. A cross correlation between AMOC and IAMV globe for each model. So you can see the correlations peak here at a lag of, I don't know, maybe 10 years, and then they drop off. Whereas for the forced component, they tend to maximize when AMOC lags. Here AMOC leads. Okay. The correlations are based on the average of the lagged correlations computed across ensemble members of each model. Negative and positive lags show that AMOC leads and lags the IAMV globe respectively. Internal variability. The dotted lines show the 5%, 95% confidence level, and they are doing a Monte Carlo resampling of the AMV variability. B is the same as in A, but for correlating each model's ensemble mean AMOC with forced AMV global for strong and weak models. So there are some strong models that produce strong correlation. There are some that are basically very weak or even opposite sign, which means the models are behaving very differently. What can you take out of it when you have models doing so many different things? I don't know. Impacts of the AMOC on ENSO and tropical oceans. Remember, I'm being very brief here. I'm not reading all the text. AMOC multi-decadal and longer variability modulates northward oceanic heat transport. These modulations are partially compensated by the atmospheric changes that reduce the resultant interhemispheric energy imbalance via Bjerknes compensation, so that the total poleward energy transport remains relatively constant. So on some low frequency time scales, you cannot keep moving heat northward. Atmosphere and the tropical ITCZ tends to move it back. So the compensation is done through a southward shift of ITCZ and the Hadley cells. So AMOC weakening is associated with those responses. So AMOC slowdown warms the cold tongue and deepens the thermocline in the equatorial Atlantic, whereas the southward shift of the ITCZ due to AMOC changes has distinct implications for tropical monsoon systems as well, including reduced rainfall over Sahel and South Asia. So it's a very complicated system. I'm glad that ITCZ has come in here, but still many details matter. Further, atmospheric tropical Pacific North Atlantic teleconnections through reduced mean meridional cross-equatorial asymmetry induce a substantial weakening of the SST annual cycle and weakening of cross-equatorial northerly winds in the eastern equatorial Pacific. So everybody is involved at this point, because eastern equatorial Pacific is where upwelling happens, and it can have very quick feedback via the Bjerknes feedback of thermocline moving SST, changing SST gradient, changing winds responding, and so on, which works on El Nino and La Nina time periods as well, right? Influence of AMOC on the South Asian monsoon. As previously mentioned, changes in large-scale atmospheric circulation induced by reductions in AMOC strength can modulate the zonal Walker cell and meridional Hadley circulations, thus potentially affecting tropical basin interactions and monsoon circulations. There is a lot more detail in the paper that I have jumped. Okay. Coming closer, influence of extratropical regions on ENSO and tropical oceans. ENSO variability and diversity can also be substantially influenced by the extratropical North and South Pacific Oceans. By applying a regional data assimilation approach in an advanced model, a recent study confirmed the strong impact of extratropics on the observed ENSO, particularly from the extratropical South Pacific. 3 of the 5 super El Nino events, so 72-73, 82-90, 82-83, 97-98, and 2015-16 and 23-24 were greatly influenced by the extratropics in both hemispheres through the North Pacific meridional mode and the South Pacific meridional mode. These two stochastic phenomena are excited by mid-latitude atmospheric variability and amplified by the wind evaporation SST feedback. I have discussed this elsewhere, but basically we are saying meridional modes are internal variabilities and often related to the ITCZ Colton complex interactions. At a 1 year lead time, the extratropics are related to the development of CP ENSO, but not to that of the EP ENSO, thus contributing to the predictability of the CP ENSO. Wow, that's a bit of a jump because we don't have too many samples to look at all those things. So TIO plus 1 degree C minus the control, so you have added some anomaly here to look at the responses, so SST anomalies, and then let's read. I tend to do this, try to explain the figures before reading the caption because I know approximately what they are, but then you have to be careful. Experiments investigating AMOC sensitivity to TIO warming using IPSL French model. The global SST changes when the Indian Ocean temperature is increased by 1 degree C within the marked box. Here, the actual TIO SST change is approximately 0.7 degrees C. Note that the warming of the subpolar North Atlantic caused by the AMOC intensification here, and variations in AMOC strength for different TIO nudging temperatures. Basically, they are using a model to look at the AMOC anomaly correlations with tropical Indian Ocean warming. So there's a very strong correlation here, and you are looking at the relative warming of TIO as well for these are sensitivity of AMOC transport to the relative TIO SST changes for the rest of the tropical ocean for years 71 to 100 and 151 to 200. Okay, so different time periods. I don't want to worry too much, but basically they are strongly arguing that TIO warming can strengthen the AMOC, which would change the temperature anomaly here and tend to negate the anthropogenic forced signal. There is a cooling here which is strongly believed to be anthropogenic forced AMOC slowdown, but on the other hand there are people arguing that anthropogenic influence here is weaker and stronger there, which would give a different explanation. People have also brought up volcanic eruptions and so on, so you can follow up. This is the schematic of interactions between the AMOC and the tropical oceans. Influence of Indian Ocean warming on the AMOC, and B is the ENSO on the AMOC, and C is weakened AMOC on the tropics. Okay, so Indian Ocean warming on AMOC, ENSO on AMOC, and weakened AMOC on the tropics. Background SST in panels A and B is the climatological mean state in the pre-industrial control simulation of the Community Earth System model, CSM, from NCAR Boulder, and SST anomaly in panel C is the difference between AMOC collapsed and active states in CSM2. Okay, lots of information, but basically you have AMOC, Indian Ocean warming on AMOC. So in warm Indian Ocean is creating perturbations to the Walker cell and also sending off signal here into the Atlantic through the Agulhas outflow, and the Walker cell here, this is basically surface temperatures and the atmospheric parts. So background states here are climatologies, as we said. So you have direct perturbations to the Walker cell pieces, creating accelerated Walker cell here. So that's the plus sign. Accelerated Walker cell here. So you have a cooling effect here, and there is a NAO plus involved as well. And this is the AMOC influence. I keep forgetting. Weakened AMOC ENSO impact on AMOC. So if you have ENSO, you have perturbations to the Walker cell, you send off Rossby waves, and there have been arguments made that some of the warming signal in the polar amplification and the sea ice melt in the Arctic and so on may be forced from here, as opposed to just the polar amplification of ice albedo feedbacks. That's important to understand the contributions from here versus local feedbacks, but I won't go into the details. But this teleconnection from ENSO to the AMOC is relatively well known. Okay, and this is the AMOC influence on the tropics. So we don't know the influence of ENSO, so a lot of unknowns. So there are decadal time scales involved here, tropical convection involved in these things, Rossby waves here, southward shift of the ITCZ here to compensate for the changes in AMOC. We already mentioned that. So the oceanic heat transport has to be compensated by the atmosphere via the ITCZ movement. That's called the energy equator for that reason. Nice papers by Tapio, Schneider, Sarakang, and so on. Enhanced Walker cell and unclear signals. Okay, so should I read this or should I try to make it a separate podcast? Maybe this is already 35 minutes, so let's make another podcast, otherwise it'll get a beat too long. Okay, see you in the next podcast.